Okay, we'll continue on. Our next speaker is Jakub. He works for Rackspace Australia as a solutions architect. He's going to talk today about changing the world with Swift. So please welcome Jakub.
Hey guys, my name is Jakub Krajcovic, work for Rackspace, and today we're going to talk about Swift, how it can be used with a project called ZeroVM to build some really cool applications and solve for some really interesting use cases. So before we continue, has anybody here heard ZeroVM, that term before? Do you guys know? Okay, well, we got a few hands. So the subtitle of the talk is Bringing the Application to the Data, and we'll get to that at the very end, where we'll basically put this typical use case of having data somewhere and an application somewhere else, and basically shoving the data to the application. We're going to change all of that. So first, let's talk about the genesis of ZeroVM, or how it actually came to be. I'd like to do this before we get to talk about what ZeroVM is. So for some context, back in 2008, Google released a research paper outlining the Google native client, or NaCl. And it was basically a sandbox technology for executing native code within the Chrome browser. So it was meant to replace or be like a substantially more secure and improved version of what Microsoft had with, I think it was ActiveX, or it was akin to the Java plugins. The idea was to allow execution of native C code, or any other code for that matter, within the browser, and basically get the browser to replace the user interface, but allow legacy applications to still work. It combines two types of safety mechanisms. First one uses x86 memory segmentation. So what that means is every NaCl, every native client instance, so to say, runs within a segment of memory and is not allowed to jump beyond that memory segment. And runtime disassembly. So this was actually something fairly new, because until Google introduced this in this research paper, any sort of software fault isolation was done during runtime, and the methods people were applying were to check whether or not the code is executing safe instructions while the code was being executed. So what Google did, and obviously that led to performance issues. That degraded the performance of applications quite significantly. So what Google decided to do was turn that around and essentially do code disassembly before the code was first executed, and make sure to check every single instruction and that way confirm whether or not it's safe to execute the code. That led to, based on the results of the first research paper, and then I think they published around 2 or 3 more research papers around the subject, it led to near native run speeds, and it was basically much faster than checking all of the instructions in line. In addition to the inner sandbox that it implements with the memory segmentation, it also implements a outer sandbox, and I had a cool picture about this, but I decided to take it out, so apologies for that. And it also checks for jumps and syscalls, and basically disallows any syscalls aside from a very select few, and that way it's able to guarantee a very high level of security for the code running within the sandbox. I think, in fact, up until some recent time ago, Google was offering a pretty big bounty for anybody breaking the security model, and I don't think that's happened yet. So now that we know what the native client is, let's talk about what ZeroVM is. This is a slide that I shamelessly stole, but it's really good because it kind of describes in a simple language what it is. So ZeroVM creates a secure, isolated execution environment that allows users to run a single application or program And service providers can leverage ZeroVM to allow their users to run applications inside of multi-tenant systems. So what this means is essentially by creating ZeroVM, or by leveraging ZeroVM, we have they used to call it a hypervisor for the cloud, or the cloud hypervisor. It's obviously not that, it's not a hypervisor. It's a sandbox, but it's a way of safely and securely executing code at almost native speeds in multi-tenant environments, and it's extremely lightweight, and we'll discuss that later on. Some of the technical details around ZeroVM. So, as we said before, it's based on the native client project. In order for the instances to communicate between each other, that's if we wanted one ZeroVM instance to communicate with another one, it leverages the ZeroVM QZ broker. So it uses network named pipes that are currently unidirectional. So it's not possible to do, as of yet, it's not possible to do a broadcast from one ZeroVM instance to all of the others, which is something that they're changing. I recently read some updates on the Google groups. And the other difference between just the NaCl project and ZeroVM is that ZeroVM is building a whole tool chain and a runtime around the NaCl. The runtime is called ZRT, stands for ZeroVM Runtime, and it provides a subset of the POSIX API, and it provides a C99 compatible environment. So what this means is that pretty much almost any C code can be directly compiled using the modified GCC compiler and can run within a ZeroVM instance. Currently, one of the biggest limitations is obviously multi-threading. It can only be single-threaded, and it's also only capable currently of addressing only 4 gigs of memory. So if the code needs to address more, that's going to be an issue. And what they also did initially was to provide a Python interpreter for the ZeroVM runtime. So what this means is that, again, pretty much any Python application, with a few caveats, of course, can run as is in the ZeroVM runtime. Now, the caveats are the biggest one is that to use it can only use the Python interpreter that's provided, and that Python interpreter has some of the basic modules statically compiled within itself. So if your Python code needs to dynamically load modules and libraries that are not currently present in the ZeroVM Python interpreter, that's not going to work, that's going to fail. But aside from that, it will run Python code just as a drop-in replacement. So a lot of people, at some of the previous talks they did in the US around this, a lot of the people questioned the differences between Chromium, the NaCl, the native client, and ZeroVM. So we've touched on a few, but I'd like to expand that a little bit more. So it retains the same restrictions as NaCl, and I have a slide about this later on. It's 7 restrictions that we can talk about during the Q&A sessions, but one of them, for instance, is that once the code, the binary, is loaded into memory, it's not writable, and it becomes read-only to prevent self-modifying code, for instance. Indirect control transfers have to use the NaCl jump and not just the regular jump instruction. So they can effectively catch them and prevent jumps outside the allowed memory segment. So ZeroVM retains the same disassembly checking, and this is the number one tenet of the security model of ZeroVM. And we'll talk about security models a bit later on, and we'll compare the ZeroVM security model to some other forms of isolation and virtualization. We've mentioned before it comes with its own runtime environment. The runtime environment is unique in that it presents a very Unix-like environment to the application. So as you'd expect, standard in, standard out, and standard error are all present, and they're represented as files. So I think it's in the form of dev input, dev output, and dev error, or something along those lines. And you can also create connections to the outside world using the Z broker named pipes, and that essentially behaves exactly like Unix domain sockets. So to the Unix developer, this would be very, very familiar with almost no surprises right there. And it also can represent files. So it's when launching a ZeroVM instance, it's possible to associate the instance with an input file and an output file. It doesn't have to be standard in, standard out. These can be replaced with a file in a similar way as if we were doing regular low-level C programming. And these files can then be read and written too. So some of the four characteristics of ZeroVM are as follows. It only allows single-threaded applications. There is no concurrency within a single ZeroVM instance. Concurrency can be achieved by running multiple ZeroVM instances, which we'll talk about later on. That's where the magic essentially happens. It doesn't have to deal with any, not just NICs, but basically no hardware devices. That's all abstracted away from, or any input-output is simply done through a file. And it doesn't present any physical file systems. It presents the C99 execution environment presents a virtual file system, which is all just like an in-memory bare-bones file system. So these four characteristics tie very well with the basic principles behind ZeroVM. And these principles are that it's meant to be very small, light, and fast. By small, the memory footprint required is just a few hundred kilobytes. By fast, we mean that the execution time, the spawn and execution time for a ZeroVM instance is less than 5 milliseconds usually. So it's incredibly fast to execute. It's secure based on the two fault isolation methods that are implied. So the inner and the outer sandbox and the inline disassembly before execution. It's open source and it's embeddable. So because of its tiny footprint and because of the way it's built, it's possible to embed ZeroVM in almost anything going forward. Anywhere you can put Linux, you can put ZeroVM. And in this presentation, we'll talk about embedding ZeroVM in Swift. But I was recently introduced to this interesting concept. So there's a company, I forget the name, but they designed a hard drive which comes in a enclosure. It's slightly bigger than a 3.5-inch drive. And that enclosure contains an ARM microprocessor, and it contains a network port, and probably some memory as well. And essentially that drive is its own little ARM computer. And so that's what we mean when we say embeddable. It's new devices like this that are coming up that present themselves as the potential vessels for ZeroVM. One thing I'd like to talk about now is how computing is evolving and how does ZeroVM play into this. We believe, and some of the people behind ZeroVM believe, that in many use cases this is the future of many types of computing problems that we'll be able to solve using ZeroVM. And to explain how we got there, let's look at what I call the path to abstraction. So before we had virtualization, we all were physical machines, and thus became known the compute unit of the one server. Now, it's interesting that that unit still kind of carries itself with us along the way, except now it's represented as most commonly as a virtual machine, but we're still contained by this one unit, and it's quite difficult to scale beyond that at some point. Past the regular virtualization that we know from VMware, we now have OpenStack, which is an amazing abstraction layer on top of physical hardware. So if you think about what idea behind OpenStack, or what it fundamentally does, it's an abstraction layer. It abstracts from all these things and presents them as objects that are malleable, and we can use them and change them and interconnect them, but we don't actually have to worry what's behind it, because we're presented with an abstract interface. However, even with OpenStack deployed, we're still tied when it comes to compute. We're essentially tied to the Nova instance flavors. Whether it be a Nova instance that takes over the entire hypervisor, whether it be something launched using Ironic, so it's a bare metal box, but we're still tied to that one atomic unit of a server. Currently, it seems that now, since Docker has hit version 1.0, it seems to be the next best thing since sliced bread. So it doesn't actually, like, Docker is cool, don't get me wrong, it's amazing, but the underlying technology behind it is really not that revolutionary, right? So Linux containers, before that we had OpenVZ, before that we had BSD jails, which we still have. Solaris introduced zones back in the day, which I remember were amazing. Unfortunately, the lack of adoption of Solaris never led to adoption of zones in a wide way. And even before that, I think it was HP with OpenVMS and some of these other, or superdomes as they are now, have the same thing, right? They basically present partitions within one server, and you can activate them or deactivate them, and it's nothing more than basically containerizing execution. What Docker does and introduces is a layer of control and a layer of automation and tools to allow us to move these containers and these resources from one place to another in a fairly seamless way. It allows us to build registries where these containers are tracked, and makes for a very, very interesting new way of scaling and a new way of building applications. I delved into how Heroku is built, and obviously Heroku's been around longer than Docker, so they essentially had to build most of the automation and tools that Docker now uses, but in its internals, Heroku is nothing more than Linux containers. So a Dynamo is essentially a Linux container, and it's presented to the user in a very transparent way. Now, along the lines of this evolution and this path to abstraction, one thing that people care about is their application. It's not the server, it's not the underlying stuff, it's the application, it's the can I scale this, is this going to run? And the people behind ZeroVM believe that ZeroVM is a natural evolution on this path to abstraction, where we literally get rid of everything else and just focus on the code that runs the application, what brings value to the people who use it. A lot of the questions that have been asked in some of the previous ZeroVM talks were around the differences between containers and ZeroVM. So I'll just briefly touch on some of these. The traditional virtual machine is, as we all know, shared hardware, dedicated kernel, dedicated OS, fairly high overhead, fairly slow startup in minutes, and the security model is essentially the hypervisor and the fact that it runs isolated virtual machines. The container is substantially more lightweight. It uses a shared kernel and shared OS, which presents itself the problem if we're capable of exploiting a kernel bug within a container and we elevate privileges, then that may possibly lead to some corruption on the host OS, essentially. There's very low overhead for containers, so it takes a few seconds to start a container, not minutes. But with ZeroVM, we believe that we take it even further. So there's essentially no kernel, no operating system to worry about. represented just a bare execution environment. There's almost no overhead, and the startup, as I mentioned, it's less than 5, is it microseconds? Microseconds, to start a ZeroVM instance. So with all this coolness, or all this speed, and the lightweightness of ZeroVM, the first application that they thought of was to embed ZeroVM in OpenStack Swift. It seemed like a natural choice, and let's look at why. So I used to work in film and 3D visual effects before I joined Rackspace, and this is a problem that I've been intimately acquainted with during several years of my career, and I'm sure a lot of you have as well. On one place, we have our storage, we have our appliances, we have our data, and it lives somewhere. And then we have compute in a different place. So physically, these two things are generally in a different location, and they're interconnected with a series of hopefully fast fiber, but that wasn't always the case. However, logically, it doesn't really make sense to have them separate. I mean, compute power is useless unless it actually operates on data. And data itself is, unless we're archiving, is also fairly useless unless we do stuff with it. So the main driver by putting ZeroVM on top of Swift was to solve this problem. And let's have a look at how they did it. So this is a very, please don't kill me if it's too simplified, simplified Swift architecture. So we essentially have proxy nodes, and the proxy nodes are the gatekeepers to all of the incoming connections. And then we have storage nodes, and the storage nodes is where all of our data lives on separate disks, and this is how the Swift architecture works. By embedding ZeroVM into a Swift cluster, we essentially put a ZeroVM instance and a little execution environment and some messaging onto the entire cluster, and it gets us to a state where we can, by using the proxies as sort of gateways and gatekeepers, and let's call them schedulers, we can essentially instantiate a ZeroVM instance anywhere our data is. So at any point when a user makes a request for a specific file, we can dynamically instantiate a ZeroVM instance on the machine where that file is hosted. It can start immediately and perform an arbitrary action on that file. In addition to that, it can also communicate between themselves. So the instances can talk to each other, and we can chain them, or we can create massively parallel execution workflows where we can process millions or billions of files, if we want, in a fraction of the time that it normally would take. Can you guys see that? It's good. This is a fairly detailed diagram, but the point to take away from here is that the beige or brownie things is the regular Swift services, and all of the blue stuff is the add-ons that ZeroVM introduces. So we essentially see the flow right here. The requests come through a parser, then they get distributed through connectors, and on each Swift node there's an executor that then takes care of executing ZeroVM instances right there where the data is. So as we said before, a ZeroVM instance can map or mount a file and access it through a dev input. That's exactly what's happening here. So if a request is made for a specific file, and we intercept that request because the proxy understands it's actually meant for ZeroVM, the ZeroVM instance will spawn itself immediately, attach itself to that file, and execute what it needs to do. So the combination of Swift and ZeroVM used to be called Swift. But I asked the developers working on it, most of them are based in Zurich, and actually no, San Antonio and Zurich are some of them. And I asked them why they changed the name. So they changed it to Zerocloud, and they changed the name because nobody could pronounce it. So they just got rid of Swift, now it's Zerocloud. And here's an example of how Zerocloud is used. ZPM is a tool that was built for the ZeroVM toolkit. That's part of the toolkit. It stands for ZeroVM Package Manager. Now, a package is nothing more than a tarball, but they call it a package. And as you can see from this workflow, you can build a skeleton package by typing ZPMU, and then you end up with a YAML file such as this. This is just an excerpt from a YAML file. File contains some definitions where you basically define the name, you define the binary that will be used to execute, and you define input files and other things. In my case, what this does is this is a MapReduce word count. So it reads all of the files in Shakespeare, which is where I uploaded. It's a Swift container where I uploaded all of the works of William Shakespeare, and all it does is it has a mapper and a bunch of, it has the mappers and then a reducer, and it goes and spawns a ZeroVM instance for every single file, counts the words, and then sends it back and gives you back a word count. To deploy something like this, you'd simply type in ZPM deploy, word count being the name of the Swift container, and the mr word count.zap. The zap stands for ZeroVM app, which is the fancy tarball, and that uploads the zap to the Zerocloud, and then you can execute using the ZPM execute command. So let's talk about some of the use cases. We spoke about changing the world initially. That's how this talk is titled, and I truly believe that at some point, if and when this technology evolves, it will present us with some very, very unique use cases and very unique solutions to problems that are fairly difficult. The first problem, not very difficult, but very common. It's kind of like the low-hanging fruit killer app. Video transcoding is a big deal, especially in the film industry, and essentially any industry that deals with large volumes of videos, whether it's turning pictures into moving pictures or whether it's taking one video format, turning it into another. This is always a problem because we have to shift around large amounts of data. And the data is binary and doesn't really compress well unless, because it's very CPU intensive to compress video, we have to use specific algorithms. So using ZeroVM, we could technically replace an entire render farm with one specifically designed Swift cluster that would be powered by, SSD fast storage. We would be able to store all of the video files in there, and that cluster itself would then become our render farm. So we would not need any additional compute resources. We would have everything in one place. And because ZeroVM can run native C code, we just need to recompile existing applications. So Pixar has an application called the Photorealistic Render Man, and if that were recompiled to run within the ZeroVM runtime, we could essentially build something like this now without too many problems, and all of the existing workflows would work. Another good example is log searching or parallel greps. This is actually something that they did over in San Antonio. So this is a real use case. I unfortunately don't have more details than what I'm going to say, but they ran a grep through 17 gigabytes of miscellaneous uncompressed log files. I reckon it's some log files taken from the Rackspace cloud. And it usually took around 5 hours to finish that grep. So they ran the same task with ZeroVM, and without any optimization, it took about 3 minutes. So that was a fairly impressive speed up by any means. And this last one, that's meant to be the mascot for the University of Texas in San Antonio. This I think is like the coolest thing I've seen in recent times. So there's research going on at the University of Texas in San Antonio, specifically around ZeroVM and use cases. And there's a bunch of PhD students that applied for research grants to go discover what this can do. And in my opinion, the most interesting one is a guy who is trying to build a distributed SQL database that is essentially backed by a Swift cluster running ZeroVM. So think of that. Instead of having data represented in rows and tables and columns, the data or a row is a file. Whether it be a text file, whether it be a binary file with metadata attached that we know Swift does natively. A unit of information is a file. And then the SQL engine is ZeroVM. And to build, so what he's trying to do is essentially build a SQL compatible interface on top of that, so that anybody who's proficient in standard SQL could type in select all from where the color is green, and potentially this could go away and search through billions of files, whether it be binary or text files, and do the right thing and return results. So there's a potential to completely change and completely redo the SQL and relational databases as we know them. And I think I'm running out of time, so apologies for that. We have one last slide. If you're interested in giving this a go, then it's all open source. And you can find the GitHub repo at github.com/ZeroVM. The homepage is zerovm.org. And the last one, zebra.zerovm.org, is a publicly accessible Swift cluster with ZeroVM enabled. So it's a Zerocloud where you can request a free account and go ahead and just go nuts and break stuff. So with that, thank you very much for your attention. And if there's any questions, I'm happy to take it.
We'll have to finish up there, sorry.
Okay.
Interesting as it is, I'm sure there's lots of questions, but thank you, Jacob.
Thank you.